Hello students, welcome back. Previously in section 1 we studied subgroups in general. Now let's go to section 2, cyclic subgroups. A cyclic subgroup is a subgroup generated by just one element. So we are talking about something very simple. Non-trivial but simple. Simple but non-trivial. But then again, you gotta know what it means by something generated by just one element. So we need some preparation. Let's begin with an element A from G, and yes, this is gonna be the element that'll generate everything, the one element that'll generate everything. And then an integer n, we define the power expression a to the nth power as the repeated application of a, e times a times a times a times and so on, repeated n times, when n is non-negative, of course. When n is negative, we do the same, but we do that to A inverse. E times A inverse times A inverse times A inverse, and so on and so forth, repeated. Absolute value of n times, so that we have positive number of times. For example, what if n is 0? If n is 0, that means no multiplication here, so we're going to get just equal to e. Oops. What if n is 1? In that case, we have one application of a, so we're going to get just a, and so on and so forth. These are just two examples. And whenever we define like this, we're going to have exponent rules like this, and like that. And the proof, well, those are tedious, so I'm going to leave those to you. For example, how do you prove the first one? Well, it's kind of like this. A to the m power times a to the nth power. Ooh, wrong key, sorry about that. So that's a times, repetition, like this. A times, repetition, like that. And then how many times must be repeated m times? And how many times must have been repeated n times? So total how many times? A to the m plus n power. Total m plus n times. We can prove like this, provided that both are positive. But then again, some may be positive, some may be negative. So we have to consider all those four cases. Both are positive. M is positive, n is negative. M is negative, n is positive. Both are negative like those. And then whenever you have negative, you have to consider repetition of a to the negative first power, the a inverse, and work out. Tedious, but it's just as simple as this. So the details are left to the students. I may give you as a homework, or maybe not even that because it's too tedious. In any case, it's going to be pretty clear. This, and that. By the way, if your starting group is an abelian group, then you can rewrite everything in terms of addition as n times a like this. E plus a plus a plus a and so on, repeated n times. Also, e plus negative a plus negative a plus negative a and so on, repeated. And if you use the second expression and rewrite these exponent rules, we're going to get these alternative rules, kind of like the distributive law, like this, and another distributive law, kind of like this. And then this one looks more like an associative law. But in fact, those are just abelian version of all these. Exponent expression and exponent rules. Okay, all good? Now let's go ahead and define cyclic subgroup. Let A be an element of G. The set of all powers of A forms an abelian subgroup. What do you mean by that? Set given like this, a to the nth power. And of course, that belongs to G. So yeah, the set builder notation is okay. It's just that this is a bit too tedious, so let's skip that. So arbitrary a to the nth power form, both for positive powers or negative powers or zero powers. Special case zero power, then we get an E, so yes, we have the identity. The question is this really a subgroup? Also, is this really an abelian subgroup? You'll have to go ahead and check these. Well defined, E is there, and inverse is there, and you need one more, abelian, because G may not be abelian, but this triangular bracket A, the cyclic subgroup, should be abelian. Let's see, do we have a proof here? No. The details are left to the students. Well, let's consider a sketch. So we have to prove that the group operation is well defined. So a to the m power times a to the n power should belong here, but by the exponent rule, that belongs to this triangular bracket A. So yes, well defined. As 2, we have to have the identity. And what's the identity? A to the 0 power is E, and that's an element of this triangular bracket A. Okay, all right. How about the proof of S3? Inverse. So arbitrary element is this form, and it's inverse. What's this inverse? If you use the exponent rule, a to the negative n power, right? And that's an integer too, so yes, it belongs here as well. So what do we have? We have a subgroup. This is a subgroup. That's the next question. Is this abelian? In other words, a to the m power, the arbitrary form, times a to the n power, same as a to the n power times a to the m power. Is that true? Yes, it is. Because if you use the exponent rule, you're going to get m plus n power. And that's the same as a to the n plus m power, because the set of integers is an abelian group in terms of the standard addition. So yes, it is abelian. So I guess we completed the proof. We checked S1, S2, S3, and also abelian. So this is not a SketchUp proof anymore, actually. I just did the whole proof. Make sense? S1, well defined, so close under the group operation, yes. And then the identity, the inverse, and then finally abelian. Yes, we have all those. So okay, this is a subgroup. Moreover, this is an abelian subgroup. And this subgroup is called the cyclic subgroup generated by A, and A is called the generator. And if that's cyclic subgroup here, this one is a finite group, then it'll have its order, number of elements. And that's called the order of A. Let's see, one final topic here. The cyclic subgroup turns out to be the smallest subgroup that includes A, the smallest. What do you mean by that? If there's any subgroup that includes A, then the cyclic subgroup is actually its subgroup. As a matter of fact, you don't really have to consider the subgroup nature because we already proved that this forms a group with respect to the same algebraic operation. And we assume this too is a group, yes? We assume. So we don't really have to meddle with the group structure. We only need to prove the inclusion. In other words, every element of this triangular bracket A, in other words, A to the nth power, belongs to H. Is that true? So if A belongs to H, then any A to the nth power belongs to H. Is this true? If yes, and there goes the proof. Make sense? Well, it's easy. When A is positive, excuse me, did I say A? N, the power, N is positive, then that's repeated multiplication, repeated application of this group operation, the first line. If N is negative, then repeated application of this group operation for A inverse. Either way, all these are elements of H, so we are doing all those group operations within H. And H is close under this group operation because it's a subgroup. So yes, A to the nth power belongs to H, whether it's positive, whether N is positive or negative, either way. So we prove that the cyclic subgroup is not just a subgroup, a very simple subgroup, a abelian subgroup, but also is the simplest, or more precisely speaking, the smallest in terms of set inclusion that includes A. And depending upon how simple and how complicated A is, the cyclic subgroups can be a little bit more complicated or a little simpler. And the simplest case, of course, is A is E. In that case, E to the any power is just E, so we have just trivial subgroup, but that's a bit too trivial. When A is non-trivial, then a cyclic subgroup will be non-trivial. Still, it's going to be the simplest possible subgroup that we can think of. Simplest possible non-trivial subgroup, excuse me. Simplest non-trivial, the simplest non-trivial subgroup we are talking about. That's cyclic subgroup. Now, in a special case, entire G is a cyclic subgroup, then we say G is a cyclic group. And that's actually a different story. It goes a lot deeper from there. And that's something we are going to discuss next week.